Hi everyone. Welcome to the Dr. Engineering channel. I'm Dr. Engineering, and this is a lesson in my VHDL series for designing with FPGA. In this series, we'll learn by doing, focusing on hands-on practice. Today's topic is the half adder, a fundamental combinational circuit that's perfect for getting started with VHDL and digital circuits. We're going to learn 3 parts. 1. What is half adder? 2. How to implement it, and 3. How to simulate it. What is a half adder? A half adder is a circuit that adds 2 single-bit binary numbers. It has 2 inputs, usually labeled A and B, and produces 2 outputs, sum and carry. Let's look at the truth table to see how the half adder works. As the table shows, when both inputs are 1, the sum is 0, and the carry is 1. This is the simplest form of binary addition. The circuit can be broken down into 2 basic logic operations. XOR, exclusive OR, calculates the sum, and calculates the carry. Now, let's implement the half adder using VHDL code. I'll walk you through the code step by step to explain what each part does. We are going to create a half adder project in Vivado, using the software we installed in the previous lesson. Let's begin by opening Vivado. Once it loads, you'll see the main interface. To start a new project, click on Create Project. A window will pop up, letting us know that we are starting the project setup. Click Next to proceed. Now, we need to give our project a name. Let's call it half_adder. Next, there's an option to create the project in a subdirectory. If we don't select this, the project files will be placed directly in the main folder. However, it's better to organize everything in a subfolder, so let's check this option. Click Next. Now, we select RTL project, which stands for Register Transfer Level. This is a common design method for digital systems. On the next screen, we choose the FPGA board we are targeting. If you have a specific board, you can select it from the list by identifying the category or family. For this demonstration, I'll just pick one randomly, since we are only focusing on simulation. Once you've selected the board, click Next. The next screen is a summary of our project setup. The project name is half_adder, and we've selected a specific FPGA. Click Finish to create the project. After a moment, the workspace will load. On the left, you'll see the Project Files section. This is where we can add our source files and simulation files. For now, we are focusing on the design and simulation parts since we're learning VHDL. In the Sources tab, we will manage our design and simulation files. You'll also see an area for properties and other information, like errors or log files, that will show up during the project process. The middle workspace is where we'll write our code. We don't need the navigator panel for now, so let's minimize it to free up space. The main area is where we'll be writing our VHDL code. Now, let's add our design file for the half adder circuit. There are 2 ways to add a file. First, you can click Add Sources in the Sources pane. Or, you can go to the File menu at the top and select Add Sources. Since we haven't created any files yet, we'll choose to create file. We're designing a half adder, so this will be a design file. Later, we'll create a test bench, which will be a simulation file. For now, let's create the design file. In the next window, select VHDL as the file type, and name the file half_adder. We'll save this file in the project folder. Click OK. Review the settings. And if everything looks good, click Finish. Vivado will now generate a template for us. The architecture name is set to behavioral, and the entity name is half_adder. We will explain what these terms mean shortly. In this step, we also need to define the input and output signals for the half adder. We already know what the signals are, so let's define them now. The inputs will have the prefix I underscore for input, and the outputs will have the prefix O underscore for output. For this half adder, the inputs are A and B, and the outputs are sum and carry. We are using single letters for simplicity and clarity. Once you've set up the inputs and outputs, click OK. Now, we can see that a source file has been created in the Sources tab. Let's open it. You'll see some comment lines at the top, and the actual VHDL code starts from the library declaration. First, we include a basic library. If you've worked with C programming, this is like including the stio.h library. In addition to this basic library, we need a library for numeric operations, which is already mentioned in the comments. Let's copy that and paste it into our file. Now, let's talk about entity and architecture. An entity is like a black box. It defines the inputs and outputs of a circuit but doesn't tell us what happens inside. The architecture describes the internal workings of this black box. In our case, the entity is named half_adder, and the architecture is named behavioral. The entity defines the input and output ports, and the architecture defines the functionality, which is implemented between the begin and end statements. For the entity, we only need to define the interface, or the ports, that describe how the half adder interacts with the outside world. To keep things clear, let's add a comment separating the inputs from the outputs. In VHDL, comments are written using 2 dashes. Now, let's describe the architecture. This is where we define what happens inside the half adder. A half adder consists of an XOR gate and an AND gate. The XOR gate calculates the sum of the inputs, while the AND gate calculates the carry. Based on this logic, we can write the VHDL code as follows. The XOR of A and B is assigned to sum. The AND of A and B is assigned to carry. With this, we have fully described the architecture. The architecture's functionality begins with begin and ends with end behavioral. We've now finished writing the VHDL code for the half adder. Don't forget to save the file. Now, we're going to design a test bench. As mentioned in the last lesson, we need an inspector to check if the circuit works as expected. First, we go back to the design source section. We need to add another source, so let's click here. This time, we want to simulate the circuit, so we choose simulation file instead of a design file. Then, click Next. Since we don't have a pre-made file, we'll create a new one. We select VHDL as the language and name the file half_adder_tb, with tb meaning testbench. The file path will be in the same directory as the project. Click OK. We keep all the default settings and click Finish. Since it's a simulation file with no inputs or outputs, we don't need to change anything. Just click OK. Once created, you'll see the testbench file under the Simulate Sources folder. Let's double-click to open it. The file contains a template, and since we don't need the comments, we'll minimize those. Next, we need to include the necessary libraries, like before, so let's copy and paste them in. Now, we have an entity and an architecture. For a test bench, there are no external interfaces, it only generates internal signals to test the circuit. The test bench wraps around the circuit like a black box. The entity remains empty, as it doesn't need any external connections. What we really need to focus on is the architecture. The idea for this test bench is to create two input signals for the half adder and two output signals to capture its results. We'll apply different inputs and check if the outputs change correctly. Inside the architecture, we define signals. In VHDL, all signals are defined with the signal keyword. In Verilog, signals are divided into register and wire types. A register holds a value over time, while a wire connects parts of the circuit, usually for combinational logic. Although VHDL uses just signal, we will name our signals using a convention similar to Verilog. Inputs will have the prefix or underscore, indicating their function is similar to a register. Outputs will have the prefix W underscore, indicating their function is similar to a wire. Next, we instantiate the half adder we designed earlier. UUT, which stands for Unit Under Test, refers to the actual half adder we're testing. Here, UUT is connected to the signals in the test bench using the port map. On the left are the half adder's internal signals, and on the right are the test bench signals. In the next step, we create a process where we define how the input signals change over time. First, we set both A and B to 0, which means low voltage, and hold them for 10 nanoseconds. Then, we set A to 0 and B to 1 for another 10 nanoseconds. Next, A becomes 1 and B goes back to 0. And finally, both are set to 1. This covers all 4 combinations from the truth table. After this, the process ends. With the test bench design complete, we can now set the simulation length to 100 nanoseconds by pressing this button and go to Simulation Settings. Click OK. Now click Run Simulation in the Navigator interface. After a short wait, we'll see the simulation waveform. Let's maximize the waveform display. In the Simulation tool, we ran the test bench for 100 nanoseconds. To fit the entire waveform into view, click AutoFit. To restart the simulation, click the Reset button. If you want to run a specific time frame, you can set it to, say, 10 nanoseconds and click Run for a specific time. Clicking 4 times will run through one full cycle. If you click Run for all, the simulation will keep running unless stopped because the process will loop itself indefinitely. However, we only need to observe one complete cycle of signal changes. Now, we compare the waveform to the truth table, and we can confirm that the output matches the expected behavior. That's it for this lesson. Practice makes perfect. If you have any questions or need further clarification, feel free to leave a comment. See you in the next lesson.